So I'm a physics PhD student. I'll just get out my notes. And at the moment, I guess quantum computing is kind of at the place that classical computing was in the 19th century. So we don't actually have computers yet. The idea for this talk is that I'll spend quite a lot of time in Ada Lovelace mode. So I'll be talking about all of the things that we could do if we had a quantum computer. At the end, I'll switch into Charles Babbage mode and talk about how no one can make gears the same size, so computers aren't actually a thing that will happen for a while yet. But, I haven't been reading those, so I can, sure, yes, okay, good. But I don't suppose that stopped anyone, so yeah. Okay. Yeah, but before that, I'll give a brief introduction to what quantum mechanics is. Bear in mind that usually it takes 4 years to learn quantum mechanics, and we're going to be doing it in 10 minutes. So there are going to be some big leaps of faith and a few small fibs that will allow us to skip some technical details. All right, so is this going to work? It does. So here are the laws of... So quantum mechanics is basically what physicists call the laws of physics, or at least the 20th and 21st century version of them. These are the laws of physics which many of you will probably have seen in school. They're Newton's laws of motion. I won't go into the details. The key things here are things which Newton kind of took for granted, but that turned out to be more complicated. So Newton was assuming that we have solid bodies, so there are these massive objects which move around as a whole. And he was assuming that things have states of motion. So when Newton was talking about bodies, he could mean things like planets, or he could mean things like people, or parts of bridges, basically anything that can move. And in Newtonian physics, the state of motion of a body is just its position and its velocity. So what that means is if we know where, say, the moon is now and what speed it's moving, then we can predict where it's going to be at any time in the future by applying Newton's laws. Okay. And note that if you have objects which follow Newton's laws, then you can build computers. So in the 19th century, Lovelace and Babbage came up with a scheme for a computer which just used cogs and gears. So all of those bits would have been following Newton's laws of motion. And if you were willing to wait long enough, you could have computed anything on that you can compute with today's transistor-based machines. Okay, so this is what we mean by a classical computer. It's something that's just a glorified version of Babbage's mechanical analytical engine. Okay, so this is about the time of the English Revolution. Newton's coming up with his laws of physics. We'll skip forward to the French Revolution and the next big scientific theory, which is that matter's made up of atoms. So here we've got Robert Boyle and Antoine Lavoisier. They did some experiments with chemistry and concluded that matter's made up of small discrete particles because it always reacts in set ratios. Okay, so at this point, people were starting to get a picture of how the universe works. We have all of these bodies, these people and computers and planets are made up of atoms, and the atoms are all obeying Newton's laws of motion. So we've got some picture for how matter's organised and how it moves around. Unfortunately, this all turned out to be wrong. So as the 19th century went past, people discovered that when you did the detailed calculations of how atoms combine to form solid objects, it just doesn't work. They kind of ignored that at the time and made excuses, but in hindsight, well, one of the things was when you calculate the pressure of an ideal gas, you're wrong by the factorial of the number of particles in the gas. So in hindsight, that looks like quite a large fudge factor. Okay. All right. So now we're at the start of the 20th century. The problems have just gotten too big to ignore. And and people throw out Newton's laws, and they've decided it's time we came up with some new laws of physics which allow us to have solid objects which don't just dissipate into a bunch of atoms. So Paul Dirac was the first person who really put it all together. Here's the first of his quantum laws of motion, and it's probably the strangest thing that scientists have ever hypothesized. So you're probably not going to believe it, and you'll think that this quantum mechanics is just some kind of fantasy. That's okay. It takes most people years to accept this happens. So Dirac's first law of motion is that whenever a system is in one state of motion or another state of motion, then it could also be in a superposition of those two states at the same time. So, in other words, if an object can be in place A and it can be in place B, and it's physically possible for it to be in either of those places, then that object could be in a superposition of both places at once. As I said, that's something that's not going to make sense. Obviously, you never see it happen for humans or planets, but when you look at things on the scale of atoms, there are lots of effects where you can only explain it if this is the case. For example, the fact that atoms stay in one piece, it's very hard to make that come out if you have electromagnetism without superpositions. So please just take that for granted for the moment. As I said, there are going to be some big leaps of faith, and at the end, I'll touch on why we don't see this for objects we're familiar with, just things which are on an inconceivably smaller scale. Okay, so here's one physical object, the computer. For convenience, we won't represent its state of motion as a whole lot of positions and velocities of cogs and gears. Instead, we'll just write down a string of ones and zeros which represents the contents of its memory. Okay, so the physical state of the computer, we can abstract to a printout of what's in its storage. So what I've done here, this is some called Dirac notation. So I've just got a 3-bit memory here for simplicity, and this computer is in a superposition of 3 different positions at once. So the cogs and wheels are in 3 different places at the same time, and that means it's representing three different states of its memory. And this is the key thing about quantum computation. We can do this. We don't just have to work on one value at once. We can work on all of them. Okay, so that's kind of the law of quantum states, that you can superpose them. The law of motion is actually a bit more sensible. It says that time passes in parallel on each part of the superposition. So here we had our initial state. We've run an increment instruction on this, and each of the 3 states of the memory just gets incremented by 1. So we end up with a superposition of that state plus 1, that state plus 1, and the final state plus 1. So people sometimes, in a computing context, call this quantum parallelism. It just means that when we perform an operation, it affects each part of the superposition independently. Right. So this is the final of Dirac's hypothesis. It's that when we look at a quantum system, we see one part of its superposition at random. So here's a physicist looking at what output this computer has produced. This time, just by chance, the physicist has seen the state of the memory 001. Now, if we perform the same computation again and look to see what it generated, we'd switch between these different values at random. So sometimes we'd see the first state of the memory, sometimes we'd see the second one, sometimes we'd see the third one. So this is the bad news, okay? The good news about quantum computing is we can compute on all possible states of memory at the same time. The bad news is that when we look at it, we throw away all but one of those states, and we don't get to choose which one we see. That just comes out at random. Okay, so there I was writing things just with 3 different possibilities. The possibilities also have probabilities attached to them. So you can write those multiplying them out the front. We've got some probability of each state, P1, P2, and P3. And then there's a state of the computer that's got that probability when we observe it. And this is an important point, and a slightly weird one. As well as just having real numbers as probabilities, we also have phases. So this is the idea of where wave functions come in. Attached with each probability, there's this phase. I'm hoping people have done some electronic engineering, so maybe you'll recognise e to the I phi as some vector that's pointing in a direction phi. This is just, so you can think of this as just a hand on a clock that's pointing in at some angle phi. And attached to each probability, we have a phase. So if you collect these probabilities and phases together, that's similar to a wave which has a value defined at each possibility for the state of the computer. So we have a probability wave which has a value at each possible state of the computer's memory. Okay, and what we're going to do in quantum computations is we are going to try to focus that probability wave on the answer that we want. Okay, so this is some observations happening. Each time we observe, we pick out some different state of memory, and each time we repeat the computation, we get a different value. So this is kind of an overview of what we're going to do. We've got some massive state of all possible 1000-bit numbers that we're trying to get an answer from. We are going to focus down this probability wave into the region of the number that we want. In practice, we're not going to get a perfect focus just on that one number. So we're going to have some sort of region like this where we focus the probability wave and we're going to get a random answer out of that region. But if, for example, the area of this region is proportional to the number of digits in the number and the number of possible numbers is the exponential of that, then obviously we've won. We're not going to have to repeat this calculation very many times, and by chance we'll stumble on the right answer. So these are probabilistic algorithms usually. We're playing bingo, but we don't have to play a whole lot of times before we find out the key to decipher or whatever we're looking for. Okay, so that's our introduction to quantum mechanics. I'll go through some applications and yeah, maybe it will become clearer or possibly it won't. Okay. So one thing that quantum mechanics let us do, it explained how we can have solid materials. So as soon as people found out how solid materials work, some clever guys at Bell Labs started thinking about how they could work differently. So this is where we got doped semiconductors and transistors, and Babbage could stop worrying about getting his gears made the same size, and we had a practical way to build computers. So yeah, that solved a lot of 20th century problems and created a whole lot of new 21st century problems and brought us all here today, right? But one thing is these transistors in computers are just acting like switches. So if you give them Babbage and Lovelace a bunch of transistors and wires and told them how they worked, the physics they understood would have been totally adequate for them to build a computer. If they'd opened up a transistor and tried to find out how the transistor worked, they would have figured it didn't obey the laws of physics. But the way you were using them as switches to build a computer was entirely classical. So people in the 19th century could have understood that, and they would have been able to anticipate everything you could do with an ordinary calculator or computer just using transistors as switches. When we do quantum computation, what we're thinking about is what we can do since we know quantum mechanics that would have baffled people in the 19th century and that they would have thought violated the laws of physics that they knew at the time and wouldn't have been possible. Okay, so we'll start. So now we'll go into full Ada Lovelace mode and start programming some quantum computers that we don't have. So first of all, just a note on control flow. if you think about the program here, where we have a for loop and the number of iterations of the loop is every number from 1 to 100 simultaneously, then it becomes clear that debugging programs like this is going to be a massive nightmare, right? Okay, so in practice, no one uses pseudocode to reason about quantum algorithms just because the control flow gets so complicated like that. So we don't attempt that sort of thing. That we use a simpler model of computation with circuits. So, oh, okay. So, So what this means, the idea is you've got inputs on the left, you've got some sort of operation happening on them, and the outputs come out on the right. So basically, the control's moving linearly from left to right, and we only do things once. Yet what I've drawn here, there's no control flow at all. We just start out with an input, and it always produces the same output. In a couple of slides, I'll get on to how the control flow actually works when we want to do things conditionally. Okay. So what I'm going to build up to with quantum computing is a description of Shor's order finding algorithm. So that's an algorithm which lets us find the order of an element of an arbitrary group in time, which is roughly the logarithm of the number of elements in the group. Now, probably the most interesting group for security is the numbers modulo n, because if you can find out the order of a number modulo n, it's fairly easy to get from that to the factors of the number. So I'm going to take the cryptography for granted in this talk and focus on the quantum aspects. But if you look for a cryptography manual, it'll explain how, if you can find out the order of a number, you can get to its factors. Okay, so when I get to order finding, I'll explain what orders of numbers means. That's just where we're heading. We're going to get there in sort of 3 steps. So the first of them is this thing called a quantum Fourier transform. The second thing's going to be what's called a phase estimation algorithm. So that lets us estimate what phase some of these probabilities have changed through. And then the third step will go to how you find the order of group elements, which is the thing that's devastating for all the public key ciphers. Okay, so this quantum Fourier transform, well, this remembers just the state of the computer. So in this case, the computer's just got memory for one number. Now, in general, this could be a superposition, but for explanation purposes, here it's just one number, and we'll think of what happens to that number. If we have lots of numbers, it'll work on all of them together. So if we have a number n and put it through a quantum Fourier transform operation, then what we get out is a superposition of all of the numbers that the computer can represent. So I've used a summation sign here to say that we're taking a sum over all possible values of k. So we've got a sum of all the numbers that the computer can represent, and the probabilities of all of those are equal, but these phases here are going around evenly in a circle. So we've got a product of n times k, so n's the input number, and what we're saying is that when we go from k to k plus 1, we rotate the phase by a fraction of a cycle, which is the reciprocal of the number of how many numbers the computer can represent. So as we go through the numbers from 1 up to the maximum integer, the phase of these goes through a whole cycle. Okay. Or if well, that's if we have an input 1. If we have an input 2, it goes through 2 cycles. So this is the sort of this is a Fourier transform operating on the probabilities instead of on the numbers. If you've done any optics or any radio engineering, I was talking about how these quantum algorithms are, in a sense, focusing the probability wave on the answer. So what you can think of this doing, you've got some probability wave coming in, then we've got some sort of diffraction object, which is these numbers being input to the Fourier transform. So if we've got some probabilities at the input, then the Fourier transforms the same relation as if we had those input probabilities as the amplitudes of elements of an antenna, and the outputs are the amplitudes of the field the thing generates. Okay, that's what a Fourier transform does. Or I've drawn it here, you've got some sort of diffraction object on a screen, and you're shining light on this object. The brightness across the screen, well, the brightness at point N on the screen is the probability that we had N in the input, and then the brightness at point K on the projection screen is the probability and the phase that we have K in the output vector here. Right. So this quantum Fourier transform operation, if we're thinking of focusing probability waves, is just that you let the wave propagate from some source to some screen. You know, it's what's happening when we go from the projector lens to the screen. That's probably a bit technical and hard to follow. Sure, so that's one component of how you focus probability waves. All right. Okay, so now we'll move on to the order estimation algorithm. Sorry, to the phase estimation. Okay, so when the thing that we're estimating the phase of is called an eigenstate. So here we've got another simple quantum circuit where we have an operation U. So U is just some operation the computer can perform. It might be increment or multiply or whatever. And here we have an input state for the computer. And we've chosen this input in a special way so that when we go through the operation, we get the same output as we input, except that the phase has been shifted by some amount. Okay, so this is something you couldn't do on a classical computer because we don't have phases. An eigenstate of this operator is something which we can send through, we can perform the operation on, and we get the same thing we started with, except in quantum mechanics, you might have shifted its phase by some amount because possibilities have phases. Okay, and if we had a superposition of eigenstates, we'd shift their phases by different amounts, and that might be useful. Okay, so what the idea of phase estimation is that we want to compute this phase phi A that we're shifting the eigenstate through. We're assuming we can prepare the eigenstate so we know what it is, and we're assuming that our computer can perform this operation. Later on, we'll prepare a special eigenstate, and the phase shift will turn out to be the order of some group element. So this is an intermediate step towards order finding. Okay, so to do this algorithm, we're going to need to do some control flow. So the way that control flow is usually considered in quantum computers is the same way it works in graphics processing units, which is that we can execute instructions conditionally. So here I've got a control bit. This is in a superposition of 0 and 1. We'll assume that 0 means don't do the operation, 1 means do the operation. Here, this is just an arbitrary input, so this input is what we're going to do the operation on. So these are the inputs. Here we've got a conditional increment instruction. So what this is saying is if this bit is set, add 1 to the number. If it's not set, do nothing to it. Okay. So since it's a quantum computer, we can have the condition bit set to a superposition of do something and don't do something. What's going to happen then? Well, okay, so here's the first possibility. We haven't changed the condition bit, so we've still got condition set to 0. We didn't do anything, so we've got the same output as we input. The other possibility that went through in parallel is that we had the condition bit set to 1, and we did the operation, and we've added 1 to the thing that we're operating on. Okay. So in a GPU, you'd have a whole lot of different processors, each of them operating on a different condition bit, in a quantum computer, we've only got one processor, and since we can have a superposition of different states, we can do it all at the same time. All right, so that's the control flow primitive for quantum computing. Is this working? Good, okay. Right, so now we're getting a bit more complicated and actually doing things. So, right, we'll go through this one bit at a time. We've seen all the bits already. So what I'm doing here's the eigenstate that I want to estimate the phase of. So that's just going to shoot through this whole circuit and come out the other end unchanged, right? And these are the bits we're actually operating on. So you can see we've initialized them at the start to all possible numbers that the computer can represent, and all those numbers have even probabilities. They've all got the same phase. So this is, yeah, every possibility the computer can do. Okay, so, and at the end, that turns into something that we'll be able to use to estimate the phase. So what we have here, well, we're doing essentially, this is the ones bit, this is the twos bit, this is the 2 to the I bit, that's the highest order bit that the computer represents. So we've got the bits for a binary representation of these numbers. And then we are conditioning these operations based on the bits. So if the ones bit is set, we do it once. Then if the twos bit is set, we do the operation twice. U squared just means do U, then you do U again. And if the highest order bit is set, then we do it 2 to the I times, or the max, or then we do it, yeah, for the number of times that's the highest order bit. Okay. So the point of all of this is that if there was a number n in the input, then we've applied this operation u n times to this eigenstate. Okay, because, well, that we've flagged each of these to the corresponding bit in the input. So the effect of that, we started with the numbers 1 to n. We get out the numbers 1 to n, but the number n has been multiplied by a phase, and that phase is n times the phase shift for the eigenstate, right? So if we have n here, then we've applied the operation u n times, and each time we do it, we shift the phase of a by phi a. So when we do that n times, we've shifted the phase by n times phi a. Okay, so so we've done some phase shift on the state which is the same as the number that was in this superposition. Okay, so well, the final step here, if you look at this, you can see that looks an awful lot like a Fourier transform. We've just got n multiplied by e to the I n phi. So it turns out when we do a Fourier transform on this state, we just get the phase. Okay, so we started out with, yeah, well, actually it's got to be an inverse Fourier transform, but that's basically the same as a Fourier transform. So we started out with the Fourier transform. You put in n, you get a sum of all the numbers with phases which vary by e to the I n k. Here we're putting in the superposition of all the numbers with the phases, and we're focusing that down to the number which is just the phase. Okay. So this is sort of the key step of Shor's algorithm. Now, in terms of optics and radio antennas, you can think of this part as a diffraction grating. So if we're going across the numbers n from 1 up to what the computer can represent, then they're rotating here with the phase phi a. So what we get is some periodic phase across all the numbers where the grid pitch here with which the phase is rotating is phi a. So if you think of the quantum Fourier transform as just propagating to a screen, we set up a diffraction grating by applying these phase shifts, and then when you put a wave through a diffraction grating, you get a beam coming out at a fixed angle, and we've set up the pitch of the grating so that the angle it comes out at is the phase shift on this eigenstate. Okay, so that's, if you're thinking of it as focusing waves, this phase estimation algorithm just sets up a diffraction grating, and then you look at what angle the probability wave gets diffracted. Okay, so that's kind of the crux strap of Shor's algorithm. The next step's to apply that to find the order of group elements. So, okay, here we'll think that X is some element of a group, so it might be a number modulo n, and we want to find out its order. So what the order means is how many times we have to multiply X by itself before we get 1. Since it's a group of a finite size, if you're doing cryptography, if you keep multiplying X by itself, then you always have to get back to 1 eventually. The order of X is just how many times you multiply X by itself, what power you raise it to get back to 1. So the operation we'll use is in the phase estimation algorithm is just multiplying by X. So the computing operation is we put in a number and we compute that number multiplied by X. And we're going to find out the phase shift for eigenstates of that. What just happened? I probably switched that off. Oh, okay, cool, good, right. Oh, okay, good. Oh, no, yeah, sure. People don't want you to know this, okay. Yeah, right. Okay, so the first question is what eigenstate we need to put in that will be an eigenstate of multiplying by X. So we want a quantum state where when we multiply by X, we just shift its phase and get out the same possibilities. So here it is. We've got the number 1, we've got the number X, then X squared, X cubed, and all the powers of X. At some point, because it's a finite group, some power of it's equal to 1, and that's the order of X. And the phases with which we've superposed these possibilities are evenly going around the circle. So as we go from 1 to X and X to X squared, we're rotating the phase through the same angle. Okay, so why is this an eigenstate? Well, if you think about multiplying this thing by X, and you remember that it acts in parallel on every possibility we've superposed. So when we multiply by X, 1 becomes X, X becomes X squared, X cubed becomes X to the 4th, and so on. And we've just shifted each state one place around the circle, and that's equivalent to just shifting the whole circle through that phase angle. Okay, so multiplying by X is equivalent to rotating this whole state through a phase, which is this angle here. Okay. So what that means is if we can create this eigenstate and we can do phase estimation to find out the angle you rotate that eigenstate to get it back onto itself, then the number of times that angle divides the circle is the order of X. Okay, and that's how Shor's algorithm works. We're gonna find out that angle you rotate X to get the powers to come back onto themselves. Okay. So here's another of the eigenstates. This is, in this one, we're going 1 to X and round 2 twice the angle at every time. So it turns out there are lots of eigenstates of this. We can go through this angle here the order is 6 and we're going through 1/6 of a circle. Here we're going through 2/6 of a circle, 1/3 of a circle, from 1 to X, then from X to X squared, and so on. Or we could go through half a circle, or 4/3 of a circle, or any multiple of 1/6 of a circle. Okay, so we're going to end up with 6 different eigenstates, and each of them is going to have a phase angle which is a multiple of 1/6 of a circle. All right. Of course, the problem is we've got to prepare one of these eigenstates before we can do phase estimation. But there's a clever trick here, which is that if you add up all 6 of the eigenstates, you get the number 1. So if you think about the angles that X and its powers are occurring in these superpositions, 1's always occurring with the same phase. So when we superpose all of these, one gets superposed in phase and it adds up. But with X, well, there's one eigenstate where it's pointing that way, one where it's pointing this way. There are eigenstates where it's pointing in 6 different opposing directions. So when we superpose all of these, those all cancel out. We've got the phases set so that the state X is interfering with itself out of phase, and this all cancels out to 0. Okay. So so the idea of the phases on probability waves is that they can cancel each other out as well as add up. So it's possible we'll have 2 possibilities in the inputs, and then they'll cancel each other out in the outputs. That's how you can get diffraction and interference, and how you can focus things. So we can just use the input as 1, and that acts like a superposition of all the eigenstates of this multiply by X operator. Okay, so here's the full order finding thing. We've got the input state 1, which is a superposition of all of the eigenstates of multiplication by X. Then we have a superposition of all the numbers the computer can represent. These are all the possibilities for the phase that these eigenstates rotate through. Then we perform the phase estimation. So we multiply these eigenstates by X, the number of times that's represented in the number up here. And then at this point, in the phase estimation algorithm, we have a superposition of diffraction gratings. So we've got 6 different eigenstates if X has order 6. And that here would mean we've got one diffraction grating which has kind of 6 cycles across it, one that has 5 cycles, and so on. And they're all superposed together. So instead of getting one angle coming out of the diffraction when we do the Fourier transform, we're going to get a different angle for each of these eigenstates. Okay, so we've got here, going back to the eigenstates, where one possibility is you have that angle, one possibility is you have twice the angle, or you could have 3 times it, and so on up to 5 times it. Okay, and so finally, when we take a look at this, we're going to get one of these angles at random. So there are 6 different eigenstates with 6 different phase angles, and when we perform the algorithm, we start out with a superposition of the eigenstates. So when we perform the algorithm, we'll get a random answer at the end, which will be one of the 6 different angles. Okay, so this is the final bit. If X has order R, which is 6 in the diagrams I've been drawing, then when we run the phase algorithm starting with the input 1, we're going to get a phase angle which is 2 pi over R, so the angle, the circle divided by the order of X, and that's multiplied by a random number m. So we get some random multiple of the phase angle that gives the order of X. This turns out, and it turns out at this point the quantum stuff's done, because we know that m and r are numbers of some moderate size. So if we're dealing with the RSA cipher, they might be, say, thousand digit numbers. And it turns out with classical computing, if you know that m over r is a fraction of 2,000 digit numbers, and you know that a decimal expansion of that to, say, 2,000 or 3,000 places, then it's fairly easy to find out what 1,000 digit numbers divide to give that decimal fraction. Okay, so if we know some multiple of 1 over r, and we know that r's only got 1,000 digits, then it's possible to find out r just with a big enough calculator. Right. I think most cryptography books will have some explanation of how you do that. How am I going for time, by the way? Oh, okay, cool. Sorry, I missed all that. Right, so I'll speed up. Okay, so I said I'd touch on why we don't see superpositions of big things. So when we look and get a result, it's called an observation, but nature's looking all the time, and that's called decoherence. So we can't actually stop. Here I've drawn some bug watching the computer, but in fact, just if it was just light coming off the computer, the fact that the light field's seen what state the computer's in is enough to mess it up. Okay, so if you think about the phase finding, say here we've got our diffraction grating in the middle of the phase finding algorithm, and if someone looks at it here, they're going to, instead of having a superposition of all possible ends, they're just going to see one of them. So suddenly our diffraction grating, which is a superposition, collapses to just one possibility. Sorry. And when you've got instead of a grating, you just have a hole, then that means that the probability wave gets spread out over all the possibilities. So rather than just selecting the phase that we want, we get a superposition of all phases and we see one at random, which doesn't work. So if you observe quantum algorithms at random points, they break. Okay, so that means we're going to need some system which we can manipulate, but which nature can't see, and that's a bit of a tall order. The only thing that really works is the spin of atomic nuclei. So we've gone from a bunch of cogs and gears down to something which is 10 to the minus 15 meters across, and quantum mechanics starts to become applicable. So the nuclei basically act like compass needles. The electrons in the atoms around them act like Faraday cages, so they're very well isolated. But because there are these compass needles, there's some microwave fluorescence which you can potentially manipulate them through. There are a bunch of clever ways you can use that. Questions whether any of them work. So this is a quote from a conference I went to a while ago. A year ago I thought that quantum computers would never happen, but there's been a lot of progress, and I now think that quantum computers are about 10 years more likely than I thought they were a year ago. Okay, that's one side of it. The other side is Clarke's laws of technology, which is when an elderly and distinguished scientist says that something is possible, he's almost certainly correct. And when a distinguished but elderly scientist says that something's impossible, he's almost certainly wrong. Okay, so I'll end off with a superposition of a cat that robbed the bank and one that died trying, and we don't know which it is yet. Good. Cool. Sorry.